Welcome to day 2 of ARCINTEX, Living Textile Architectures. I'm so pleased everyone, you could all join us again this morning. So we've got another packed schedule today. We'll start with our keynote event, and then we're going through to have 2 more sessions, followed by another event in the OHM. So to begin, we have our keynote panel event, which will follow a similar format to yesterday. And so it is my huge privilege to welcome to the stage Professor Phil Ayres. He's the Professor of Biohybrid Architecture at the Royal Danish Academy. And I think what Phil brings is this incredibly unique perspective on the digital, on the physical, and on the biological, and bringing those together through some incredible research projects that he's led. And I think for me, he's been this huge inspiration in terms of thinking about textiles in a completely different way, and thinking about the opportunities of textiles have in both the digital realm and also engaged in biology and the physical realm.
Well, good morning, everyone. Everyone here and also everyone online. It's an immense privilege to come and speak to you today. Thank you very much to Jane and the ARCINTEX network for inviting me. I've been aware of the ARCINTEX network for 10 years. And of course, there are many colleagues of mine at CITA that have had a much closer relationship. This is my first time here. I hope it won't be my last. So I'm going to talk about, as Jane said, some of the research projects that I've been involved in. That, and in a way, I'm actually going to avoid talking about the biological aspect, because ARCINTEX talking about textiles really allows me to kind of give the space to the unsung heroes, really, of some of these projects, which are textile logics. So, is that not moving forward? Well, then I'll do it here. Let me just check. Okay, if I do the up and down, great. So, This is a diagram from one of our papers, braided workflows from, I think, around 2018, where we're looking at really why it is textiles are interesting. They have this incredible versatility, and they span these axes here between scales that are sub-millimeter all the way up to scales that are producing architectural artifacts that are greater than meter scale. They allow us to work with synthetic materials and natural materials. And they also, in terms of their production, allow us to work with highly engineered methods all the way across to handcraft. So in this way, textile logics really have a quite incredible versatility. But if we move away from kind of perhaps the kind of positivist understanding of the material itself and start to think about how textiles actually allow us as humans to start to occupy environments that can be incredibly hostile or alien to us. Textiles also have this tremendous ability to both be used as a way of representing and storytelling, and also constructing identity. Textiles have also had this amazing relationship to other foundational technologies such as computing. And then we also see how textiles can also be the foundation for building social structures that might be incredibly empowering or equally incredibly alienating and exploiting. And then from an architectural perspective, I think what's really interesting is the way that textiles have found a new vocabulary, moving from essentially interior finishes to now, especially from the mid-20th century, moving towards technologies that allow us to use them in quite extensive structural modes. So really we can start to think about textiles as being a kind of foundational technology. They're fundamental to human development over time. And if we think about beyond just their material aspects, and we start to think about the way that the terminology of textiles has become woven and embroiders itself into the tapestry of our language. You see how I seamlessly knitted that in. So yesterday we had some fantastic presentations talking about the kind of idea that fibres really set the scene for multiple scales in terms of textiles. Of course, the fibre presents a threshold between scales that we can enter that talk about physics and chemistry and biology that produce those fibres, so really kind of moving down into scales. The work I'm showing really starts at the fibre and moves up towards architectural scale. And really, this kind of idea about the fibre and populations of fibres being organised in different arrangements is really what gives textiles their emergent properties, their emergent functional and material properties. So I'm going to talk about 3 different kinds of textile logic through these 3 EU-funded projects. So we've got braid on the left, we've got Kagome weaving in the middle, and this new project that hasn't actually started yet, which will be looking at non-wovens. So if we begin with the Flora Robotica project. So this was a 4-year project. The project was really looking at how we can build symbiotic relationships between unconventional robots and plants as a way of trying to grow architectural structures. What you're seeing here is part of an evolved controller where we can place a set of target points, and the evolved controller is controlling light to get the plants to touch those targets. And so this, as a kind of control mechanism, was really an idea about how it is that we might be able to use the plant and begin to weave it within structures that are more architectural. The project really takes on board a kind of horticultural idea about the trellis. And the trellis is a really nice kind of garden motif that talks about the idea of anticipation of colonization and the anticipation of biology starting to structure an environment. But there's also a kind of longer and kind of alternative history looking at arboreal practice in relation to architecture and the use of living plants to create architectural space. So within this, and to kind of contemplate the idea that as we're growing plants, they also need some kind of structure. You know, sometimes it takes them, depending on the plant species, it can take them time to develop the tissues required for self-support. We started to look at logics where we might be able to grow the structure together with the plant. So this is where braid really became a very useful logic to begin to work with. And so we started to kind of do our braids, and we were thinking, well, we're making some very elegant things here. We've got a logic here of branching. But we started to wonder, could we move that a little bit further? Could we start to develop the language of this to start to suggest greater complexity? And of course, as architects, the key thing here is that through our material investigations, what we're doing is we're building artifacts that create a set of relations that what we want to do is learn how to encode those into modes of representation. Because as architects, this is our primary mode or our primary methodology. Okay, representation allows us to both speculate, but it also allows us to specify. It allows us to have internal conversations that develop design, and it allows us to also communicate those designs to others. So we went into this big effort of trying to instrumentalize the logics of braid into computational models. And here what we're doing is we're taking a graph approach. So we've got nodes and we've got edges. The edges are weighted. The weighting talks about the number of braid elements. And here we start to see how they begin to distribute. And then what we do is we wrap a mesh around that. And it's a quad mesh. We inflate the mesh. And then what we have here is a tiling dictionary. And the tiling dictionary essentially sets up all the relations of different crossings that we can have at the crossing level. And then we can populate our mesh. So you see here, not working. But over here on this one, this is a naked mesh, and here we've got a populated mesh, and then we can render that out to give us our braid. Is that giving? So having got the logic, that then allows us to start to begin to simulate these things. And actually the bit I wanted to show you here was, try and play that. So having been able to define the way in which we can instrumentalize that logic, the next step is then starting to look at designerly ways that we can begin to engage to start to explore different morphologies. And so you see here we've got a very simple block method, and then on top of that starting to simulate the idea of different material properties within this. So you can start to see here we can introduce weavers that have different stiffness capability. So this starts to give us a really rich representational space for exploration. And you see here some of the kind of results that we're getting here. These are not renders of hope. These are renders that actually embed a principled braid that could be manufactured. The trouble is, there was no manufacturing platform that we could use to produce this. So that became the next step. Having produced all sorts of viable methods and morphologies and topologies of braid, how might we approach their construction? So this was a first approach, the idea that we're using distributed robotics. One of the interesting things here is that then your fibers can start to have all sorts of other functionalities. You can begin to embed things that have sensors, that have actuators, and so you can start to build essentially functionalized braids. One of the restrictions, of course, is their path following. And unless you've got a method for being able to modify the path while they're running, you're always going to be stuck with a fixed topology of your braid. So then a different approach was to start thinking about a modular technique. And this takes us back to kind of quite early technologies of braiding machines. The difference here being that at these points, what we have are little switches. And these switches start to allow us to move the braiders into different configurations. So you see here, starting to move together with more and more bobbins. And I think, there we go. And so what we arrive at here then is essentially a modular braiding machine. We can break this down essentially into each one of these separate modules and start to combine them into different configurations. And then you see here a simulation where we've got something that is actually weaving and then bifurcating, producing four different strands here. And so really through this project, you know, in terms of the textile aspects of it, I think what we're doing is we were contributing to a kind of expanded and enriched understanding of what we can produce with braids. The biological aspect then was about introducing plants that could start to navigate their way through this, and there were further modes of modelling that were starting to look at how it is that produces local stiffening. And so really our contribution, I think, on the braid aspect was essentially this workflow. So as we move into the Fungal Architectures project, our partners here, 3 academic partners, 1 industry partner, an amazing team based at CITA. And really the thinking in this project is looking at mycelium as a material that we can produce construction elements from, but that might also have computational capability. I'm not going to go into the computational aspect here, but really the aspect that we're looking at is producing a construction system where essentially we can think about producing mycelium elements as a form of casting technique, And rather than thinking about the casting element as being something that is throwaway, might we be able to make it as something that is a stay in place and can also act as a reinforcement? So you see some initial studies here where we're getting some very nice colonization. The stay in place mold and reinforcement really starts to become a bound part of the unit of the composite. And just to kind of talk about why it is that Kagome is interesting. This is Shigeru Ban's Centre Pompidou in Metz. And you can see that essentially the roof has a Kagome type pattern occurring up there. But one of the key things in terms of the design here is that this is the projection on the floor. So you've got a regular hexagonal lattice, but you've got a complex geometric roof, and what's happening is they're projecting that lattice up onto the roof to understand the geometry. And then they're actually cutting that geometry into the timber. And when you start to move into these kind of highly complex, doubly curved glue lams, that results in a huge amount of machine, or a much larger amount of machine time, a larger amount of waste, and a larger amount of cost. And this is really because what you're doing is you're putting the design intelligence into the geometry. Now, if we look at really the craft of Kagome, the design intelligence here is actually put into the topology. And what you're doing is you're using the topology together with the material properties to create a self-supporting framework where the geometry emerges out of that relationship of interlacing, of the material properties, and then the topology that you're working to. And this is where you really have to acknowledge Alison's work. And Alison's been a key collaborator since around 2016, 2017. This was our first paper written together. And I mean, her work has really exposed this, this kind of understanding about how topology drives the geometry. So you can see here that what we're using here and what is different from the Centre Pompidou, where you're cutting geometry into doubly curved elements, is here we're achieving complex geometry but doing it with completely straight strips. And from an architectural perspective, that produces an incredible rationalization in terms of fabrication. And so you see here that to gain the elliptical geometries, what you're doing is you're using lesser sided polygons, and to gain hyperbolic geometries, you're using greater sided polygons. And then the distribution of these allows you to start to create all sorts of different morphologies. So you can see on the left here the idea of how this maps into the computational data structure of a mesh. We've got a regular mesh, that gives us a planar geometry. If we introduce a singularity, that gives us an elliptical geometry. If we introduce a heptagon, that gives us a saddle geometry, anticlastic. And then we can start to distribute these to start to give us any form that we desire. So one of the challenges here really was how it is that we can create principled topological adjustments to meshes. And there are some very simple mesh operators. We're using one that is called flip edge. You can see what we're doing up there. S is the singularity that we want, and we want to turn that into a 5, not a 6. So the valence really refers to the number of edges that are coming into the node. As we flip that edge, you see that we generate the 5 that we want on the left, but the collateral damage is that we've generated a 7 above it, a 7 below it, and a 5 next to it. Yeah? So and what we want is we just want a single 5 in that zone. So the way to achieve that is actually we take a region and then we flip all the edges within that region. And so that leaves us with a singularity of 5 and all the other nodes unadjusted to a 6. So what does that mean in terms of then design? Well, it allows us to just go in, pick a node, and actually start to change the topology of the mesh and to have that relaxed directly. So this becomes a really useful tool for us to be able to very quickly prototype different geometries. And geometry becomes important then because, of course, when we think about how these geometries might be embedded and situated in the world, they start to create different kinds of affordance in terms of relationships to their environment. And so what you see here is really a completely principled mesh design. You see these zones here, where we've got a greater sided singularity, is introducing the saddle curvature. We've got fives distributed just up there, where we're wanting the elliptical curvature. So having got the representational technique together, the issue really then becomes how do we start to map this to materials? Because of course, as we move towards architectural scale loads, we end up in situations where, unlike the basket weaver who's working with bamboo, which has a degree of stiffness, but it also permits local pliability, when we're at architectural scale, those kinds of materials are very rare to come across. So we've done forays, again, with Alison and also Adam Orlinski and Moritz Heimereth from Bollinger Grauman, looking at the idea of a really textile logic to achieve this, where we're using a cementitious fabric, which is cut and then woven. And I mean, we get to the point where we've actually got a load-bearing structure, but the kind of disappointment with this was really in its assembly, because you've got no stiffness to the material until you wet it and you cure it, and therefore you need to have all sorts of structures to be able to essentially hang and drape your construction against. Subsequently, what we've done is we've developed a technique, and this actually goes back into a patent from the 1980s, produced in Denmark, for something called compressed wood. So here what we're working with are solid beech. These particular ones are 40 by 20. You steam it, it goes through a compression cycle. The compression cycle essentially concertinas the fibers. And then for a period, while you still have a high moisture content, the wood becomes incredibly locally pliable. And so that allows us then to assemble these weaves, which essentially directly transfer the basket making technique into load-bearing structure. Furthermore, there are no mechanical fixings and no chemical fixings. So this is completely held by itself. One of the differences is through this scaling is that unlike basket weaving, where the material stays elastic, essentially in this process we're doing a very local plastic deformation. And so we're not relying so much on fibre to fibre friction like baskets do. What we're relying on is essentially a jamming technique of these mirrored reciprocal triangles. And what becomes amazing about this as a structure, let me move forward one. What becomes amazing about that as a structure is it actually rattles. It's a bit loose, and when you load it, it kind of finds its, and you can see here that it takes really quite a significant amount of load. I have to admit that the loadings there are unequally distributed. And so this really sets up a kind of set of opportunities in terms of our design space, and starts to allow us to kind of project really quite a different language of architecture, which I'm not going to go into just at the moment. Just to show you, I see I'm running out of time, just to show you some of the developments there. So really, I think through this practice of trying to build the representational techniques, it actually gives us a platform for a kind of quite interesting enrichment of very familiar pan-cultural techniques which anyone can master, but to be able to see that you can master it at this scale and it's directly transferable to that scale, I think could be tremendously empowering. Oh, let me turn that off. I'll just move it on. So then to the kind of, there might be one more coming. So I don't know how we turn the sound off there. Okay, well then I'll just skip over it. So, so this is then looking at the non-woven, and this is going to be very brief because the project hasn't actually started. It starts 1st of November. These are the partners involved and the principal investigators. And the project is Fungitaria. So in this project, what we're seeking out to do is develop a portfolio of mycelium-based engineered living materials. So you know, from yesterday, I realised that everyone's absolutely up to speed on what ELMs are about, and what an amazing audience to be speaking to about that. And you know, where many conventional ELMs really look perhaps at the idea of a polymetric matrix, where you're seeding it with living cells. Here what we're doing is we're using mycelium essentially as the matrix, and we're introducing bacteria into that to create a co-cultivation method. And so part of the project is also about developing this modular and generic platform for producing the ELM. So, I mean, some motivations for why it is that we're working with mycelium. So it can be grown on a wide variety of organic substrates. It has highly tunable properties. It's got robustness in harsh conditions. There's rapid growth. Can be produced using a diverse array of fermentation techniques. It's got sophisticated environmental and adaptation mechanisms. And there's also a thriving cross-disciplinary research community looking into them, which is great for sharing. Oh, beg your pardon. And then the motivation for working then with a bacterial partner is, of course, they're highly amenable for synthetic biology engineering, as we saw from Tom's presentation yesterday. There's extensive engineering toolboxes existing. The thing that I find very interesting here is that the introduction of particular bacterial species can start to affect the topological growth of mycelium. And so this becomes, you know, for me, the kind of common thread through all the projects, because really the focus through textile logics is less about geometry and much more about topology. So this kind of affecting of the topological growth, there's also this relationship to having a kind of spatial temporal chemotaxis that can be controlled by fungal genes. And so, you know, that really talks about an idea that these two fungal partners in co-cultivation are actually in conversation with each other. And so just to start, you know, the project hasn't started, but nevertheless I've started to kind of begin sketching out some kind of modeling techniques here, starting to think about environments with different gradients and how that might start to affect branching, either arresting branching, or it's a little bit subtle here, but you can perhaps make out that there's actually just linear threads here rather than the branched threads over there. And really this starts to kind of set the platform for the way in which we can begin to think about the distribution of bacteria as a way of creating heterogeneous materials. So materials with essentially different structure, even though it's a non-woven, which essentially is structurally indeterminate, we can still talk about making meaningful changes to structural behavior at this scale, which I find very interesting. And in some ways we can see that there's an analogy back to the work with the braiding, where essentially instead of using a servo motor as a way of being able to change the topology, we're replacing the servo motor with a bacteria. So there's some really interesting literature as well that starts to talk about how it is that we can begin to look at the analysis of the mechanical properties of these kinds of materials and also in their heterogeneity. So we'll certainly be working with those. But to kind of conclude, I want to talk about some of the other aspects of modelling and some of the challenges that I think this presents to conventional architectural practice as we start looking towards living textiles. So, you know, if we think about conventional architectural practice, we have this kind of idea that projects are composed of kits of parts that are predefined. And they have assembly logics that are predefined. But if we're starting to talk about the idea of living architectures, the idea that we can predefine things really doesn't fit, because something living goes through a continual cycle of becoming. It begins to challenge how it is that we might be using our computational technologies and also the types of modelling techniques that we're using. So here, you know, we've got in conventional practice a kind of idea that BIM really is about being able to control and specify everything down to the final screw. But we need to start thinking about completely different models if we have things that are living, and essentially the very material basis of our architecture is going through a development cycle. So this also then begins to question some kind of quite fundamental fictions that we've told ourselves as architects for many, many years. The fiction that there are very clear delineations between design, construction, and occupancy. And I think this image, you know, captures it perfectly. The Elbphilharmonie, and it says fertig, right? So it's complete. And this is the moment at which occupation begins. So there's this kind of framing of the idea that construction's finished, now the building is complete, it's finalized. But actually this is the point where a building starts to really transform. By introducing living complexes, it starts to open up a set of extended boundaries that we might not even be conceptualizing within our design models. So we see this, you know, from the work of Susan Simard, you know, where she's been mapping mycelia as the wood-white web and really beginning to understand the kind of complexity of these networks that extend far beyond our mapping capabilities. And a kind of suggestion here about an architecture in Florobotica, you know, that starts to just acknowledge the idea of fragments that become essentially entangled in the architecture. And so this kind of really begs us as architects to start widening our understanding of what an architecture can be. But we do have models for architectural practice considering these kinds of things. And a very interesting one comes from John Soane. So in his practice, he had a very interesting relationship with Joseph Michael Gandhi. And he would commission Joseph Michael Gandhi to paint the Bank of England as a ruin before construction had even started on the Bank of England. And I think this kind of talks about the idea of an architect that can begin to envision an architecture that can occupy many, many different states across time. It's not necessarily that what I'm advocating for is that everything ends up as a ruin. Advocating more for the idea that we can conceptualize different states of an architecture. And he takes this, you know, to a really interesting degree in his book here, Crude Hints Towards an History of My House in Lincoln Inn Fields, where he's projecting the idea of an archaeologist in the kind of mid-20th century discovering the ruins of his house and trying to figure out who it was that occupied it. But we also see it in more contemporary visions here. So Peter Cook's Veg House, the idea that, you know, you start off with a very conventional architectural partie, but what he's doing is he's exploring the idea of a productive corruption by biological entities that take that architectural vision and transform it into things that the architect could never have planned. Doesn't mean that the architect doesn't necessarily get involved and not curate those, but it certainly takes it into a level perhaps beyond what the architect could have envisaged initially. And then the final slide talks about perhaps both a metaphor and perhaps some certain types of modelling that I think we need to start engaging with. So the metaphor comes from Harold Fisk's work, where he was mapping the movement of the Mississippi River. And what I find fascinating about this is that despite the form of the Mississippi River taking on these completely different geometries over time, we still understand it as the Mississippi River. Yeah? The standing wave that has energy and material that passes through it still allows for an identity, and an identity that can change and yet still have, at a different scale, an identity that is preserved. And I think that starts to move us into having to kind of consider other kinds of modelling logics, and this is where, in particular, I'm looking now very much towards the kind of modelling of complex systems and the kind of the models that they use as a way of being able to study dynamics of complex systems, which I think is going to be absolutely critical towards developing a much more enriched understanding of our living architectures. Thank you very much for your attention.